Hi folks, and thank you very much for coming. It's great to be here. It's great to talk about some of the things that we're doing at NGINX. And specifically, I want to talk about some of the efforts that we're doing to take the core technology in NGINX and build out a fabric for highly scalable, highly dynamic, and extremely fast microservice applications. As Joe explained, I'm Owen. I look after the product roadmap and strategic direction for NGINX. I'm based here in the UK, so very happy to connect with people later on. I'm in the same time zone. It's always a challenge when the company is headquartered either in San Francisco or engineering teams in Moscow, so time zones are a challenge. So it's great working with a local audience. What I'd like to talk with you today is about the shift that we are seeing in how enterprises and web monsters are building web applications. I'm going to focus on the networking problem. That's an area of research and development and product features for NGINX. I'll talk about some of the architectures that we've come up with, how they're being used in production, how we're moving them into production. And I'll finish off, I'll wind up with what we describe as the fabric model architecture, the kind of crown jewels that addresses the challenges that we've been seeing. So, the big shift. The monolithic approach for building applications has served the industry very well for many years. And I'm sure I don't need to go in a lot of detail as to what this means. I hope that's something that's familiar to you. You are here at a Microservices conference after all. The key approach, the key aspect of a monolithic approach that I want to highlight is the way that applications are built and connected. With a monolith, your core application, when it needs to access another service, another component, that component is linked directly in with the core application. It could be a big C application where the code is dynamically linked. It could be built in some sort of scripting language where you pull the code in at runtime. But the point is that all of that code together, your code, the third-party code, the other modules that you need, are all run within one large single monolith. And our industry has built tooling, monitoring systems, and best practices around how to deploy and manage and scale this type of application. You may have heard of the cattle and pets analogy. A monolith is a pet. It is a piece of code, it's an application that you deploy and you care for. You look after, you care about its life cycle from birth through to the middle, through to the time when it needs to be decommissioned. But the challenge with monoliths centers around the challenges of agility. When you need to make a change to that monolith, you may need to apply a new open source module for one of the components. You might want to pull out one part, plug another part in, or just a simple code change to your own application. That's very, very disruptive. It involves rebuilding and retesting the entire monolith. And for that reason, organizations are looking at a much more decoupled approach, known as microservices. Microservices, you could regard them as SOA on steroids. In our industry, things go round in cycles. SOA was very much the method of the day 10 to 15 years ago, and it fell out of favor and it's come back again. We're seeing the same approach with decoupled API-driven applications emerging with microservices. Microservices give agility, they give the decoupling, again, benefits that you'll be familiar with, but they also bring a number of challenges. Challenges around a new, unfamiliar application stack. To buy into the microservices approach generally means buying into an entirely new stack, starting from the bottom with containered applications like Kubernetes, containered platforms like Kubernetes, through to new monitoring tools on the top. Microservices bring security problems that you wouldn't have seen in a monolithic application. And they bring big performance issues as well. If the application is not architected well, then a single performance problem can ripple through very quickly in the way that it wouldn't with a monolithic application. The point of microservices is that the code is disposable, like cattle in the cattle versus pet analogy. The key thing to make a microservice application work well is not to focus on the code, but rather to focus on the APIs, the interconnects between the different bits of code. If you focus on that, if you track performance by looking at the APIs, by looking at the network traffic, if you focus on optimizing the network traffic, that's the first step to optimizing the availability and the performance of your microservice application. NGINX has been adjacent or directly in the microservice market ecosystem for many years. NGINX, quick straw poll. Who's familiar with NGINX, the open source project? All right, pretty much all of you, which is great. So you'll know it as a high-performance web server, as a gateway for applications. You'll know it as an application accelerator. NGINX, the open source project, brings together a range of different means to help you construct an application and to act as a shock absorber in front of potentially fragile infrastructure behind web servers, application servers, and the like. Its lightweight footprint, its reliability, its ability to handle spikes of traffic with a range of different protocols has made it a key part of modern applications. If you were to go to Docker Hub now and look at, on Docker Hub is a registry of official and community-managed Docker container images. If you were to go there now, the NGINX official image, the one that our team manages, is right at the top in terms of number of pull requests, in terms of stars. Clearly, the industry and the ecosystem is seeing and recognizing that NGINX is a perfect fit when it comes to the challenge of managing traffic within a modern container-based application. Whoops. NGINX, the company, also has an extended version we call NGINX Plus. Show of hands, anyone familiar with NGINX Plus? Okay, almost nobody. This is common. People think of us as an open source project. We're not. There is a large team behind the open source project that is supported, financed, and driven by NGINX Inc., our company. It was established by Igor Sysoyev, the original author of NGINX, the proxy. Igor is still with us, leading an experimental team on our engineering team in Moscow. There's some really cool new technology coming with his fingerprints all over it in a few months' time, specifically aimed at microservices, but I'm not going to talk about that right now. NGINX Plus is our commercial build of NGINX, and it focuses on a slightly different problem to NGINX, the open source project. NGINX Plus is securely targeted as a load balancer, as an ADC. We initially created it with a view to creating a software alternative to a traditional hardware ADC, an F5 or a Citrix or a Radware or something similar. But we're seeing that the technology that we built into that is beginning to be a perfect fit for some of the problems that we're trying to solve in microservice applications. NGINX Plus brings in native service discovery, critical in a microservice environment, brings in much richer monitoring, authentication capabilities, APIs to help it be configured. And bundled up with that, it's supported by our engineering team. We have a stream of managed updates to make it much easier for our users to deploy, and it is one of the key focuses of the development of the work of our development team. And NGINX Plus exists as a way of bringing new features to market, and the commercial activities that we undertake with NGINX Plus allow us to continue to support and develop the open source project. So there's a symbiosis there. If it wasn't for NGINX Plus, the open source project wouldn't have the degree of support and the momentum that it currently has. As part of our work with NGINX Plus, we've been looking at the architectures that can be used to build and deliver microservice applications. And we started with our own reference application as an internal project to spec out and experiment with the technology that we had. We built, the details aren't important, but we built a photo site just because we could build a photo site with something with a number of different self-contained components. We built it using Docker containers, running on AWS in a polyglot fashion. Components are written in Java, in Ruby, in Python, in PHP, and in Node. We followed, at least roughly, the 12-factor app design, and we've used this as the test bed for understanding what are some of the networking challenges that microservice applications have, and how can we feed that into our roadmap and the solutions that we're building. The key challenges that we identified centered around networking, and this is what I'd like to share with you today. First of all, when you deploy a microservice application, as you recall, things are linked together by APIs. You need to find API endpoints, and those are not easy to predict or easy to track when those APIs are instantiated by microservices running on a fabric such as Kubernetes. For that reason, a common approach is to use a technique called service discovery. When a container is deployed, then the presence of that container is identified in some fashion, pushed into a service database, and then other containers or other applications can query the service database to find where is the photo resizing container, where is the inventory controller, where do I go to get user database. For a microservices application to work effectively, you need to have a fabric of service discovery so that one container or one service can locate where other services are. The second challenge settles around load balancing. If you want to scale your microservice application, or you want to put a degree of redundancy in place, you need to deploy multiple instances of the same service. So you can scale out, or so you can handle failures or slowdowns of individual instances. Traditional load balancing methods, so round-robin DNS, for example, aren't effective in this sort of environment, where you may find that one container is failing and is perhaps running much faster, returning error messages, than another container which is actually doing the work. It doesn't give you the flexibility. It doesn't support situations such as connecting to monolithic, stateful applications. Developers need a lot of control over how traffic is routed and how operations such as blue-green deployments are automated and managed. And finally, microservice applications are often deployed in multi-tenant environments. This means that security is critical to network traffic. Unlike a monolithic application, where all of the data is transferred from component to component through function calls, in a microservices environment, the data is transferred from component to component, often in plain text across the local network, making it very, very vulnerable to snooping, to types of attacks, to interposing another container in place of the one that you wish to talk to. So encryption at the network layer is critical. SSL is the obvious choice for that degree of encryption. VPNs, we experimented with VPNs within a microservice environment and found that the complexity they added, difficulty around debugging and tracking traffic made them just not a good fit. But SSL is computationally expensive. Performance and latency is something which you'll have to deal with when you build your first microservice application. And if you want to do SSL, for example, for all of your calls from one component to another, there is a big hit in doing that. Consider what happens when an application running in container A wishes to talk to container B. It first talks to the service registry to find where container B is. It then instantiates some sort of HTTP object. It makes a network call to container B. Running over SSL, that network call involves at least 7 packet messages back and fro. If your local network latency is in the order of 5 or 10 milliseconds, just setting up that connection could give you a latency of 30 or 100 milliseconds. And when you're in the situation where one call coming into your application fans out to hundreds of calls through the application to assemble the data that you need to respond back to the client, then all of those little additional steps of latency can add up very, very significantly. And a naive approach to microservices can be very, very heavily impacted by this latency. If you want a good solution to these challenges, the attributes of the solution should include service discovery, they should include robust load balancing, and they should include some sort of persistent but reliable and easy to manage encryption on the transmission layer. And we looked at 3 network architectures as we spec'd this out and built it. The very first we describe as the proxy model. This essentially is the traditional mode of using a load balancer in front of an application. Focus on internet traffic, use the capabilities of the load balancer as a shock absorber to manage spikes of traffic, rate limit, apply ACLs, perform security, and then find a way of dynamically connecting that load balancer to the very, very fluid and turbulent environment behind. We've released this in a variety of different forms. One of the most commonly used is an Ingress Controller that we've built for Kubernetes that uses NGINX at its core. And what these systems have in common is there is some mechanism of monitoring the internal microservice environment and pushing the location and the topology out to the load balancer. This model focuses solely on incoming traffic. The load balancer is informed as to where the microservice instances are by a range of different methods, and then you can use the load balancer as the protection, as the shield in front of the fragile, brittle microservice application. You get all the benefits of a load balancer. You get SSL termination, you get traffic shaping, you get a web application firewall, you even get caching if that's something that is appropriate. And with an ingress controller, such as the Kubernetes ingress controller, you get a dynamic link between the state of the application and the load balancer. In the case of Kubernetes, we use an agent that tracks the current deployment of containers and dynamically reprograms the load balancer. Without any restarts, it can use an interface in NGINX Plus, or it can rewrite configuration for NGINX open source and restart the software. But you can also use a DNS-based interface so that the load balancer can query the service registry to locate where services are. If this is something that you'd like to look into a little bit more, look us up on GitHub, grab the NGINX Kubernetes Ingress Controller. Plenty of information on our blog talking through the deployment patterns. I'm currently working with the lead engineer who built this, and we are transforming this and elevating it to a fully supported solution. So if this is something which you wish to prototype and to deploy in production, there's already a substantial number of production deployments using both our commercial software and the open source software, and within the next few months, this is something that will be fully supported by us, by our engineering team and our support team, should you wish to deploy it in production. Option 2 for load balancing topologies for microservice applications, we describe as the router mesh. The router mesh provides the service discovery and the advanced load balancing that you saw in the proxy model, but also gives you more control for internal traffic, allowing you to do things like implement a circuit breaker pattern. In the router mesh model, we place a dedicated centralized load balancing tier within the microservice application. This load balancing tier, this router, acts as a broker for all of the internal traffic within the application. When microservice A wishes to talk to microservice B, all it needs to do is to talk to the load balancer. The central load balancer performs the service discovery. It performs load balancing. It performs the SSL. This gives you a lot of control over the internal traffic, but it still suffers some of the performance issues with SSL. Every time your microservice application wishes to talk to the load balancer, because it's not stateful, it will need to create a new SSL connection to talk to the load balancer across the open network, and that, again, can give you a performance issue. This model The Deis router, Deis is a common open source platform. The Deis router works like this. It uses NGINX open source. Our own microservice reference architecture can work in this fashion using NGINX Plus. By embedding the load balancer directly within the application, it gives you more control over how different services communicate with each other. And it allows you to implement some more advanced patterns, things like a circuit breaker pattern. One of the challenges that you'll find with a microservice application is that if one particular microservice fails, and they are prone to, microservices tend to be less reliable and less robust than monoliths. So if an individual service fails, the effect of that failure can ripple through the application. In a perfect world, you would implement some sort of circuit breaker pattern to isolate that failure. Think of an application like the front page for a service like Amazon.com. Amazon, a single hit to Amazon can trigger up to 1,000 internal microservice calls to build that page. Figure out who you are, figure out your recent purchases, give you recommended items, give you a list of your recent orders. All those things are implemented using internal services. And Amazon do it well. If one of those services were to fail, that doesn't take the entire page out. The circuit breaker ensures that the rest of the page continues to render, but the piece of the page that's controlled by that service is isolated and is elegantly blanked out. So if they have an issue with their people who bought this also bought that microservice, then hopefully you won't notice that because the application is architected using a circuit breaker so that the content that's provided by that microservice is replaced with some sort of holding content, maybe just a blank bit of text. So that circuit breaker pattern allows you to recover if an individual component fails. And you can implement that using health checks against the individual services to identify if services are failing. You can implement it by controlling the retry behavior on the interior load balancer. You can do that with great flexibility on NGINX. You can implement it by caching responses so that if the upstream service is failing to respond, in certain circumstances you may be happy just to return the last good response. So having control over the interior load balancer allows you to create some innovative solutions like this. But the router mesh model still suffers from performance issues because of the requirement to SSL encrypt all of the traffic for each individual request across the network. The final model that we've developed we describe as the fabric model. It provides the benefits of the router mesh, but also implements persistent SSL connections. The fabric model is architected around an approach of embedding what's sometimes described as a sidecar load balancer, so an instance of NGINX Plus within each microservice. It communicates to the microservice across a local network or even across sockets, so there's no need to encrypt that traffic, but it gives that microservice the knowledge as to where other components are located. It does the style of load balancing that's appropriate for each individual microservice, and it acts as both the forward proxy to communicate with other microservices and the reverse proxy to accept traffic from other microservices on behalf of the local service. So instead of having a centralized router, which is a potential point of failure and a potential bottleneck, this architecture allows you to distribute and scale the load balancing and routing mechanisms just as you distribute and scale the application itself. How does it work? Well, if we look at the architecture without the fabric model, if one service, so our investment manager instance, wishes to locate and talk to another service, then that involves doing a DNS request to identify where that other service is, creating an SSL connection with the 7 steps back and fro in order to make the connection, writing the request, tearing it down. No state is stored between requests, of course, so it relies on techniques like round-robin DNS if you want to scale your microservice out. Building in health checks is complex. It's commonly done by having an external health check agent that then updates the service registry if a component is down, and that introduces latency. It means the system can be very slow to respond to errors, and it makes it difficult to automate things like dynamic upgrades or blue-green deployments. With the Fabric model, by embedding an industry-class load balancer within each individual service, it's able to take on those network tasks. And the architecture that we've created involves running NGINX within the service. When the microservice wishes to talk to the user management service, for example, then it can use NGINX Plus as the central point of control. And quickly, we'll talk through some of those measures. Service discovery. NGINX Plus handles service identification. It pulls and caches information from the service registry. It has an asynchronous resolver, so there's no performance hit of doing that. And supporting DNS SRV allows you to dynamically control the weights and the state of individual services. Passing a request to NGINX Plus is done across a local network or even local sockets. So by its nature, it's secure because it's contained within the container. And then creating the SSL connection and load balancing it is deferred to NGINX Plus. NGINX Plus can maintain persistent SSL connections to other remote microservices. That eliminates the performance hit of the SSL handshake. NGINX Plus can implement a range of different load balancing schemes. Depending on the application, some schemes are more effective than others. Round robin is basic, but doesn't take into account the performance of individual services. A least connections approach is commonly used, but least connections suffers the problem that if one of your microservices were to fail, typically it could return error messages much more quickly than a working microservice could return the correct response. Then the effect of least connections is you suddenly start hammering the server that's failed and grabbing error messages very quickly, when instead you should be identifying that it's failed and winding traffic back. Our slow start capability, the health checks built into Plus, allow you to identify those sorts of situations and work around them. The persistency gives you performance, the range of different load balancing, the ability to use session persistence allows you to cope with the vagaries of different applications. The persistent SSL connections give you a significant performance boost. In our own application, we saw a 77x performance improvement over fast local connections by maintaining persistent SSL connections as opposed to having to create them on every single request. And of course, you can implement advanced patterns like the circuit breaker that we described before. So, what I'd like to share with you is the research that we've done, the Fabric model that we've prototyped. This model will be released as an open source solution on GitHub in the next few weeks, month or two. Right now, we are working with a number of customers to deploy this in production. It's going through trials with these customers. We're looking forward to successful production deployments in the next month or two. And we've demonstrated internally, and we are demonstrating with those customers, its effectiveness in improving the performance of microservice applications, in dealing with reliability issues, and in giving you detailed status information on both sides of the picture, both at the external Ingress load balancer and the interior load balancers. So, as we close, the point that I want to leave with you is that in order to deploy a successful microservice application, the first thing to think about is how to get the layer 7 network right. And the key is in layer 7. You're not deploying a simple layer 2, layer 3, get the packets to the right place network. You need to look at things from layer 7. You need to put the intelligence into the application and the fabric to ensure that the internal traffic, the API requests, are routed to the correct services, and you have the means to support the operational tasks that you wish to use as you manage the life cycle of each individual container. We have a proven Ingress Controller solution NGINX and NGINX Plus have been used in this fashion for years. It's something which, demonstrated by NGINX's popularity on Docker Hub, something which is mature and reliable and can be deployed both with NGINX open source and NGINX Plus. We can help you to architect an internal load balancing solution. This is something which is an active development within our team. It's something that we're very happy to bring on customers and partners as either development partners or early adopters. And I'd love to connect any of you with our team if that's something which is of interest to you. And just to close, if you thought that NGINX was just a web server, it was just an accelerator, it was just an application gateway, there's so much more to what NGINX, the project, and NGINX, the company, is able to offer you to help you build high-performance, highly scalable, highly reliable, and easy-to-monitor applications. So, if you fancy coming and joining us and learning from the developers, from the leadership team at NGINX, and from many of our users and our customers, then save the date and come and find us in Oregon later this year. So folks, thank you for your time. I appreciate there's not time for questions, but I and my colleague Ronan will be around and very happy to talk with you afterwards. If you need to get in touch with me, Owen, O-W-E-N, at nginx.com, and very happy to follow up afterwards. So again, thanks for your time, and thanks for your attention.